In this lecture, we are going to focus on proportions, doing the same thing as we did last time, but this time we're going to review what you did to determine a proportion. So let me remind you what the test stat would be. So the one that you're going to use looks something like this. You may not remember all of these symbols or anything like that, but let me write down a couple of other things first. P hat, that's this little thing, is the sample proportion. And then P is the population proportion. And then sigma P hat equals the square root of PQ divided by N. So this takes probably the one that I'm not going to bother writing Q sub P hat. I'm just going to always use this formula directly. PQ slash N. Like so. So there's our test statistic. Everything else works the same except a couple of things that I'll point out when we get to them. Q, you may remember, is simply 1 minus P. Then the way the the hypothesis test works, there was one little addition at the beginning that you used to determine if the sampling distribution of the sample proportions was normal, and that's where we need to determine that NP, n times P, is greater than or equal to 5, and we need NQ to be greater than or equal to 5. And then that would be like step one of any of these processes, to make sure that we're dealing with normal distribution. 2, we list H0 and HA. Everything else works the same as with the other one. We list our level of significance, our alpha. As before, determine critical values. Not so critical. Well, the critical region is still determined by P, but when I say determine critical values, I'm talking about Z sub 0, Z0. I'm going to do the examples just like I did before. I'm going to do one using the classical method and then one using the Pvalue method. Number 5, let's see, determine rejection regions. There may only be one, so I probably should put parentheses around that. You may only have one critical value as well. Then we compute the test stat. And that's what I'm talking about here. Like so. And then you make the decision. All right, so we'll follow those steps. I have a couple of examples, but I'm going to do a total of 4 examples, but I am only going to do 2 examples, but each of them I'm going to do twice. So let's start with the classical methods first. So as an example, suppose I have the following claim. The population proportion is less than or equal to 18%. So what are the things that we're given? Sample. We have the sample proportion was 20%. The size of the sample was 1995, and we want to test the claim at alpha equals 0.10. So before I do the classical method, the classical method and the p-value method both deal with similar things, but what I want to do is there's one part in these problems that has to be done first, whether you do the classical or the p-value method, and that's to check for normality. If the inequalities don't hold, then you can't even do the test. So let's first start with NP and see how big that is. That's supposed to be greater than or equal to 5. Well, the N that I had was 1995, and the P that I had was 0.2. So it's probably not a bad idea to convert all of your answers to decimals unless you like working with percentages on your calculators. So for this one, I get 399. So that one checks. Now let's do the other one. NQ also needs to be greater than or equal to 5. And this is 1995 times 0.80. And I need that to be greater than or equal to 5. Let's go ahead and do that one. I get 1596. And so I can now proceed to run the test because I know that we're dealing with the sample proportions being normally distributed. So let's go ahead and run our test with the classical method first. All right, so let's first get this in. And this is another thing, actually. I probably should have waited to write. I should have written this down before I said I'm starting the classical method, but nonetheless, let's go ahead and write our null and alternative hypotheses. So I get P is less than or equal to 18%. This is the claim. And then H sub A is that P is greater than 18%. And so we can see that we have a right-tailed test. Now start with alpha equals 0.1. And what I'm going to do then is use the table to get me my Z0 value. 0.5 minus 0.1 equals 0.4. And then my Z value, well, Z sub 0, awaits whatever I find in the table. So let's go ahead and look at that. So for 0.4, let me see where I can find it here in the table. The closest I have are these two entries here, 0.3997 and 0.4015. Since 0.3997 is closest, what do we have then? If I go across the row to it, I'm at 1.2, and if I go up top, 8. And since we're dealing with a right-tailed test, my Z naught is going to be positive 1.28. Now let's go ahead and calculate the test statistic. All right, our p hat was equal to 0.2, I believe, yes. Our p hat was 20%, so that's 0.2 minus 0.18 all over the square root of the p, once again, is 0.18, 0.18 times 0.82 divided by 1995. And for that, I get approximately 2.325. So when we draw a picture, the start of this critical region occurred at 1.28. That's a horrible looking dot, but nonetheless. And then this Z value that we have is definitely inside of the shaded region. So we reject H naught. As I said, I'm going to redo the previous example. Using p-values. You're going to have to be careful with your p's here. You're literally going to have to watch your p's and q's in this problem. Lowercase p's are going to be the proportions. P-values is a different thing altogether. It represents amount and area. I mean, it's a proportion of its own, but we're not thinking of it directly in that way. So once again, let's go ahead and see what we have. We still would have to check NP is greater than or equal to 5 and NQ is greater than or equal to 5. But we did that last time, so I'm not going to bother doing that again. And then the test stat is going to be the same thing we did before. And that is Z equals P hat minus P all to the square root of PQ slash N. I put in the numbers last time. You can review what I had. But now we only need 2 decimal places here because now we are going to use a table and try to determine the area. Since it's a right-tailed test, we're going to try to determine the area to the right of 2.33. So let's go to the table and see if I can find the row-column intersection of 2.33. So I have 2.3, here's my row, and now let me move over to 3. So I get 0.4901. Now recall what the table gives us. The table gives us this value in here. So the table gave us 0.4901. We want what's out there. That's the p-value. And so to get that, we're going to do 0.5 minus 0.4901. And I think that's 0.099. 0099. I believe. Let me do a quick check on that. And I get 0099. And let me check my alpha then. I forget what alpha was. It was listed in the last problem, 0.1. So if you recall, alpha equals 0.1, p is equal to 0.0099, and we can definitely see that p is less than alpha, so that means we reject H naught. Let me do another example, 2 ways just like the previous ones. This time I'm going to do a two-tailed test. So we have a claim that the population proportion is 5%. Now we have our sample, looks like the following. We have a p hat was equal to 6%. And we have an n equals 200. Now we want to test the claim at 0.05. And then we'll start with the classical method. All right, remember the first thing we need to do is NP has got to be greater than or equal to 5, and NQ is greater than or equal to 5. Our N was 200, and our P is 0.05. So I believe that's 10. And so it checks for that one. On the other hand, we have 200 times 0.95. Remember, Q is 1 minus P, is greater than or equal to 5. Obviously, this one's going to be greater than or equal to 5. But nonetheless, let me finish this computation so you can see this is 190 is greater than or equal to 5. And sometimes you can tell just by looking. Or I looked at the previous computation and I saw the other computation is going to be even bigger than that, so I knew it was going to work. All right, so we have ourselves a two-tailed test because we have our H sub 0. That's where we have P equals 5%, and then our H sub A is P does not equal 5%. Remember, this was the claim right here. And the bottom tells us we have a two-tailed test, not left, but two-tailed. Well, in the classical method, that means I've got to take whatever alpha they give me and divide it by 2. So my alpha over 2 will equal 0.025. And so if I want to make use of the table, I have to do 0.5 minus 0.025, that equals 0.475, and now I'll go ahead and use the table to find out my Z value. So let me pull over to the table, and now I'm looking in here, 0.475, there it is right there. That is 1.96. I'm in the 1.9 row, and I'm in the 0.06 column. So 1.96 is my Z naught. Now let's calculate the test statistic. Here we have Z equals P hat minus P all over the square root of PQ slash N. P hat in this case, what was our sample proportion? 6%. So we have 0.06. P was 5%, 0.05. Divided by the square root of P is 0.05 times Q is 0.95, and then times N, which was 200. And from this, I got approximately 0.65. And so let's go ahead and draw our picture. Actually, this is not, remember, since it's a two-tailed test, we have plus and minus. So when I go and look at this, to be honest though, you're almost always only going to be checking one tail or the other. Here is 1.96, and the other one is the negative. And our Z value, though, lands outside of there. So because of that, we fail to reject H naught. And to finish out this, we will redo the last example using the Pvalue method. So if you recall, the difference here is that we first compute the test statistic. That's the P hat minus P all over the square root of PQ slash N. And I did those in the last example. For this, we've got a 0.65. And then what I'm going to do is use the table to give me the P value. So if we look at this, let's go to the table. 0.65 is what I'm looking for. My z is 0.65, so 0.65. I got 0.2422. Now remember though, what it gave me was the following. That amount is 0.2422. Now, last time when I did a p-value that involved two tails, I think I misspoke, so let me see if I can fix that up. To get this piece, I know I've got to take 0.5 minus 0.2422. And let's see what we get for that. I get 0.2578 for that. Now, I made a mistake last time. I compared that particular p to alpha over 2, and that's perfectly okay, except the definition of p is the following. The p-value actually equals, in a two-tailed test, it actually equals this part and this part. There's actually two pieces. Since they're the same size, though, I can simply do 2 times the 0.2578. Now, if I do that, I get 0.5156. Now I don't have to do alpha over 2. Our alpha was equal to 0.1. So with that, at least I believe, no, the alpha was 0.05. Let me fix that, 0.05. It's clear that p is way bigger than alpha. So this means we fail to reject H naught.